So in this lesson, I'm going to look at the unit vector. So what is the unit vector? Well, there is just a standard definition for it. It's where a vector that has a magnitude of 1, for every vector, there is a parallel vector with a magnitude of 1. So basically, every single vector has a unit vector. So let's do an example just to cement this in. What are the components of the unit vector q parallel to the vector p? Okay, so we've got a vector p, that's 3, 4, and we want to know what the components of this one is here. Okay, so what we're going to have to do first is work out what the magnitude of the vector p was in the first place. So how do we do that? Well, let's work out the magnitude. We did that earlier, so that's just the square root. This is just the 3, 4 again. 3 squared plus 4 squared, because we just did the 1, 3, 4 triangle. This just comes out as a 5. Okay, so the magnitude of p is 5. So from our definition here, we can see that for every vector, there's a parallel vector with a magnitude of 1. Okay, so what is the magnitude going to have to be 1 when this magnitude is 5? Okay, well, it's going to have to be 1/5 of that. It's going to have to be 1/5 as long to be 1. So we know that the components of each part of this will be 1/5 the size of them for p, because that makes sense, because it's been. So what does this actually look like? So when we're looking at q, so we know that q magnitude is equal to 1. So what about the q components? Well, we know that's going to be 1/5 or whatever it was for p. Wait one sec, I'll just draw it all out for the sake of argument. Okay, so we know it's going to be 1/5 of p. So what does that mean? It's going to be 1/5 of 3, 4. So what does it actually equal as? All you do is just take this 5 and divide each number by it. This becomes 3/5 over 4/5. That's it. That's your final answer. It's pretty straightforward. But the only problem with unit vectors, you might be thinking, well, you know, why do I care? Why am I being told this? Well, it's to do with how useful it is when you can scale things down and up. So just take this for example, down. If you had to calculate the direction of a 1,000 meter straight line, a kilometer line, you could either go from one end to the other end and then check the direction, check how far you'd gone and where you were, or you could take that down. If you knew it was completely straight, you knew it was traveling the same direction, you could just scale it down to 1 meter. See here, I've just drawn this in already. So if it's that's a 1,000, we said in the example. Just for the sake of argument, 1,000 meters. So 1,000 meters long, you'll check where it is, or you could scale it down to 1 meter and go, okay, well, this is pointing in this direction, and here I've said, it's going, northeast. So there, from that, you could see that, okay, well, now I know I've only had to measure 1 meter, and now I know what direction I'm going in. So it's quite useful for that, and other things where you want to be able to scale down is a technique called normalization.